In the last video, we introduced the rotational equivalents of the kinematics quantities: angular displacement, angular velocity, and angular acceleration. In this video, we will explore the rotational equivalent of mass. You're probably wondering why we even need a rotational equivalent of mass. The answer comes from looking back at Newton's second law. Newton's second says the overall force on an object is related to the acceleration that the object exhibits. The greater the mass, the harder it is to achieve a desired acceleration. So mass is a proportionality factor that tells you how hard it is for an object to undergo linear acceleration. Now what we need is a corresponding proportionality factor for rotation, something that tells you how hard it is for an object to undergo angular acceleration. Mass is not sufficient for this. Consider this skater. Her angular acceleration clearly increases when she draws her arms in, but her mass is unchanged. For rotation, we have to account for both mass and shape when discussing resistance to angular acceleration. And that isn't even all, because the difficulty of rotating an object also depends on the location around which it is rotating. A wheel rotating about its center will be easier to spin than a wheel rotated eccentrically at a point not at its center. Fortunately, we have a quantity that encompasses all these factors. It's called moment of inertia. It is symbolized by the letter capital I, and it has units of kilograms meters squared. Moment of inertia always has to be calculated with respect to the center of rotation. In this video, we will just demonstrate how to calculate the moment of inertia. We'll talk more about what it means and how to use it in future videos. It's possible to use techniques of direct integration, but to save time, we could more easily use a table like this. Each shape has its own moment of inertia, and it's easy to calculate based on its mass and other geometric factors. This table is reproduced in your textbook. For instance, if you have a solid sphere of mass 2 kilograms and radius 0.5 meters, you could just plug that information into the equation for moment of inertia of a solid sphere, 2mr squared over 5. Solving, this would give us 0.2 kilogram meters squared. Sometimes we run into more complex shapes. These can frequently be broken into simpler ones, and each of their moments of inertia added. For instance, this windmill has 3 blades. Each blade has a length of 3 meters and a mass of 9 kilograms. We can treat each blade as being identical to a rod rotated about one of its ends. So all we have to do is take the moment of inertia of a single rod, that's 27 kilogram meters squared, and multiply it by 3 to get the moment of inertia of 3 rods all rotating at their endpoints. That works out to 81 kilogram meters squared. In this video, we introduced the notion of moment of inertia, a measure of the difficulty of spinning an object. While we have discussed the calculation, we haven't yet explored its significance. That will be shown in the following videos.